this is generally applicable, right? Okay, let me say applicable always. These probabilities always hold, right? Regardless of how you get your omega fp, right? Okay, the first thing of course is that if A is a subset of P, of B, right, then PA must be upper bounded by PB. There is no way that a bigger set can have a smaller probability, right? Now what is this notation? I think we are saying this for the first time, right? This C like elongated C, if you will, right? This means that the set A is contained, the event A or the set A is contained in the set B, or the event A is right is contained in the event B, right? If so, this in probability jargon it means that if A happens, B always happens. But the reverse need not be true, right? B can have more points or something outside of A, right? Then A must be, the probability that you assign to A must be no bigger than the probability you assign to B, right? Which is obviously true because you have the concept of set difference now, right? What is this? The set difference in such cases is clearly the set of points in B but not in A. So this brings us the this is A, this is B, this is the set difference. So B excluding A, this is basically what? B intersection A complement, right? That B intersection A complement must have, and this is obviously in F, remember, right? Because of the rules of F that says if A and B are in F, all of these things that you derive like this must be in F again. So this B intersection BAC must have zero probability. And what is P of B? P of B also is P of A plus P of B intersection A, sorry, B difference A, right? Again this follows because B and B, in this particular case B and B difference A, right, are exclusive, right? Sorry, A and B difference A are exclusive. So therefore this additivity has to happen and be equal to P of B, right, because the union of A and B intersection A is B. So therefore P of must be greater than equal to 0, right? By the way, we will get a lot of bounds in probability theory, right? I came up with this phrase which kind of sounds cute. It abounds in bounds, right? It's one subject where bounds are rife, right? Right from the first lecture to the last, we will be looking at bounds. Or I mean, not to say that we do it every class, but it will keep coming up periodic, very frequently, right? Much more frequently than any other maths class that you may have taken, right? So, so just be prepared for inequalities of this kind, right? So this maybe we can put some numbers here. So this is the first, right, important statement that follows from the axioms. Let's see if what other things we can say. Clearly P of A complement must be, right, probability of the complement must be equal to 1 minus PA. I do not think we need to spend more time, this is so obvious that, right, we do not have to. Remember omega is what? A union A complement always, right, for any A, and they are by definition exclusive, and therefore this follows. The most non-trivial result. In general, for what is this probability of PA union B for any AB, not necessarily exclusive. This is the standard result that, right, is quoted in all books in the first few, somewhere in the first few pages, right. Right. How do we get this? How do we write this? It all depends on writing this A union B, right, as a union of exclusive events, right. So if we start off with just two events A, B, right, this A union B is this portion, right, which includes all the elements in A and or B, right. So you count all of these points obviously only once in the union. So what is A union B? It's basically A union something. If I want to say A union, it's basically this portion. If I want to write this union of exclusive events, right, this portion is also written as B difference A, right, even when A and B are, when B is not a superset of A, right. So what is this set difference in general? It consists of all those points in B which are not, right, which are not in A. So that this statement is, right, always true, regardless of whether A is a subset of B or A is a superset of B, right. In other words, this A union B is A union B A complement, right, and then which are mutually exclusive. This A is, right, exclusive of BAC, right, and therefore so I don't have to worry about the intersection when I just go back to the axiom. I just write this as P of BAC, right. And then from this it's easy to derive, right, that this must be PB minus PAB, right. So in general this P of BAC, whether it's this form or this form, P of BAC is PB minus this is maybe a result worth saying all by itself, right, because how do we get this? B itself is counted as the union of this and these two mutually exclusive parts. This is BAC and this is BA or AB. So clearly PBAC is PB minus PAB. So if you plug this in here, you get this result. So this is a very important, useful result, right, which works for any pair of events A and B. And not only that, it can easily be generalized, right. I can look at A union B union C. How do I generalize it to A union B union C? How do I generalize to A union B union C? So as a corollary or whatever extension, so here what we do is you first write this A union B union C as, let's say you first write this as A union B union C, right. You look at it like this for any ABC, not exclusive, right. Put the colon out here. then this P of implies this P of A union B union C is P of A union B plus P of C minus what? By that, what is it? Minus C intersection A union B, right. I will just write it like this. We do not need to put the intersection sign, right. We have used that convention from all, everywhere we have been using that convention, right. So now this we expand using that. So this is PA plus PB minus PAB. This guy comes here, then of course the PC comes here, minus this, I am just putting another bracket for this portion, right. This is now P of what? C, P of AC union BC. Now note that yesterday we talked about distributive law, right. C intersection A union B is AC union BC. This is the easiest form of the distributive law to remember in some sense. This is multiplication over addition, right, which all real numbers and complex numbers, right, they obey. The other one is a little harder, right, that union distributes over intersection is not so intuitive, but intersection distributing over union is, I think, very, we may latch on to that, right. So if you take this thing inside, C inside, you get exactly this, and now this once again can be expanded using, right, that probability is expanded using that. So finally what do you get? I am not going to write all the steps, so you tell me, do it and tell me, what do you get? You get PA plus BB plus PC minus PAB plus BBC plus PCA, all of those with a negative sign, and then you get plus PABC. Where does that plus PABC come from? That comes from here. AC intersection BC is just ABC, right. If you draw a Venn diagram, that will become very clear. AC intersection BC is ABC. So therefore, to cut, one problem that I have with this board is that, right, I do not know how the recording, I want to say this on camera, it does not matter, but it's right, this the bottom portion is not that usable. Anyway, I will go write one more line and hopefully it will PAB, PA plus BB plus PC minus PAB plus PBC plus PCA minus plus PABC. So you can see a pattern emerging, right, from this. If you want to extend this to the union of 4 events, what happens? You get something very similar to this, right. It will be an extension. The individual probabilities will come first, right, but the danger is, right, I mean if you in the exclusive case all of these joint probabilities will go to 0. So these guys, right, are the only guys that will survive when you have a collection of exclusive events, right. But when you have non-exclusive events, right, then all these other terms start to come into the picture, right. And the next step would be, this portion would be the same, but instead of PABC you will get ABC, BCD, CD, A and so on, right, that all those will come on the plus sign, and then you will get a minus of PABCD. So it will keep, the extra terms will come with a plus minus, alternative plus minus sign, right. It is called the inclusion exclusion principle. I do not want to write the general version of it, right, you can go look it up, right, inclusion exclusion principle, right, for the union of n events, right, in general. So it can be extended, and but it becomes quickly somewhat, right, unwieldy, shall we say. So once again, now let us appeal to a bound to help us out, right. Now these bounds are helpful, of course, only, as we will see, right, only if the number that we come up with is a meaningful or useful number, right, the upper bound or lower bound. So in this case, let me write the bound out and let us see how useful it can be. The union bound. Union bound on the union of some n events ai, which need not, or the probability of the union of n events ai, they need not be exclusive, right, any n events. Right, exact calculation is messy, as we just now said, right. Exact calculation means that we need the intersection probabilities for not just pairwise, right, terms, we need intersection probabilities of of events taken 3 at a time, 4 at a time, and so on, right. So how do we simply write a simple upper bound on this? It turns out that this union can be no bigger than, than what you would get if all of them were in fact mutually exclusive.
Summation of probabilities.
Yes, so the summation of probabilities is going to be an upper bound, right, that this portion out here is an upper bound to the union, the probability of the union, right. Sorry. With equality if and only if what? The ai are pairwise exclusive. That is, any two events in this collection must be mutually exclusive. Every pair of events that you pick up from the ai must be exclusive. If you want to actually formally prove this, you have to start with the first pair itself. Let's say a1 and a2. P of a1 union a2 is all clearly upper bounded by P of a1 plus P of a2 because P of a1 a2 is going to be non-negative, right. Then you extend that by induction, you get this. So this is the union bound, very useful in many examples, especially in bounding some error probabilities in communication and so on, right. But the utility of this union bound, when does it become totally useless? If the right hand side is bigger than 1 or even equal to 1, right, then the union bound is useless. So it's useful only when the RHS is strictly smaller than 1. You know that any probability has to be, right, smaller, at most 1, right. So there is no point in saying my upper bound is 2 or 3. Upper bound is 1, period, by definition, by construction, right. Sorry, this should be useful. All these mistakes that I make, right, fine, let them be on camera because it shows up the problems of talking and and writing at the same time, right. You start a sentence in some form, right, and then you write the opposite of what you intended to write, and then turns out that you will go and make a correction. Doesn't matter, right. We want these lectures to be as realistic as possible, right, not some kind of anyway. Okay, so so I think maybe I'll pretty much okay, one more point, maybe I have a couple of minutes, so maybe I'll just conclude that, right. Supposing you have a partition of omega. So this is another property which I have stopped numbering anyway, but anyway, let me not write a number. What is the partition of omega? Clearly this, in the discrete case, right, the elementary events P of omega I are the elementary events omega I are a partition. A partition is where you have a collection of mutually exclusive events, right, which the union of which make up what you are trying to partition. So this ai, let us say I equal to 1 to n is a partition of omega when what? Two things have to hold, right, when one ai are pairwise exclusive, right. That is, any pair of events out of this collection have to be mutually exclusive. By the way, this notation I equal to 1 to n, I suppose, right, you by now you have gotten used to it, right. It means just the entire collection A1, A2 up to An, right. It is a short form of writing, you can use this freely, right, whenever you have such things to talk about. And I wish they would use this more often in the DSP course as well, but they do not use it, right, for some whatever reason, right. But this is exactly the same kind of thing that you have been studying since you looked at discrete time signals and so on, right. So they are pairwise mutually exclusive, and secondly, the union of all of these AIs is omega itself. Now note that, right, AIs can be arbitrary events in this as long as they satisfy these two conditions, right. They need not be elementary events in this in the discrete case. The discrete case, obviously, right, you cannot right, you have taken it down all the way to the elementary events, right, and those will obviously be a partition. But what about the continuous case, right, omega being having an uncountable infinity of events, right, which is somewhat sometimes called continuous, right. There also you can partition with a discrete, with a countable number of AIs, and sometimes this n need not be finite, it can even be, right, infinity, countable infinity, right. So in this case, then any event B which is constructed using this omega must be expressible, right, as a union right, as a union of BAIs of the, right. So basically what we have is, we have, I hope this is okay, so I have A1, A2, A3, some A4, okay, let me stop with this. I have A1, A2, A3, A4, so I have some, let us say, right, something like this. The omega now is this outer rectangle, right, it has been partitioned using these 5 AIs. Then if I take some B, any B must be like this, right, it must sit inside omega maximally, right. So what can you say about B? B is basically the union of BAIs I equal to 1 to n. It need not involve all n, but it cannot involve any more, right. It need B, you may not get, right, B may not need all of the AIs to make it up. It does not matter, some of those BAIs may be 5, may be empty, right, maybe the, right, which is, but that is, it's okay, right, you can always take a union with 5. So, and it is important to note that this B, all these BAIs are exclusive, right, and therefore this P of B is what? Is the sum of P BAIs, right. So we will pick up, I mean, just this last thing, maybe I will say it again tomorrow in tomorrow's class, since so I have n n divisions of omega basically, right, n non-overlapping divisions of omega, and union, of course, this is. So whenever we have a situation like this, right, in pictorially it is drawn like this, right, A1, A2, A3, drawn like this, then if I have any B, any event B, right, obviously the event B has to live again in omega as a subset of omega, right, and therefore it has to intersect the AIs. So for any B, any subset B which is in the Borel field, of course, sorry, which is in the sigma algebra F, right, for which we want to assign a probability, and that, so we have B will be the union of BAI, right. This may sound trivial, but it is actually not, right, it is actually, right, a very useful thing, a way to construct this B, right, using these intersections, right. This idea of making up this B using intersection, using the parts of B which intersect each of the eyes. It's a very useful idea, right, especially in more complicated experiments, right, as we will see as we go along. So here of course we have flattened out everything. We have, right, a single flat representation of omega, the AIs and B and so on, right, but later on when you look at two-stage experiments and so on, right, one experiment and then feeding another one, then this kind of idea will be you know pretty much the only way you can approach, right, this problem, right. So you construct this B, the overall event B, as a union of BAI, and because the AIs are pairwise mutually exclusive, right, BAIs will also be exclusive. You can clearly see from the Venn diagram that BA1 has no intersection with BA2 and so on, right, okay, and therefore so since BAIs are mutually exclusive, the probability of B is now the summation of BAI, right, using our additivity formula. So this rule, which I am stating formally, right, just using AIs and using this a part of the course, I am not going to do any examples right now, but you should be able to relate the later examples to this result, right. So right now we are just concentrating on writing down some intuitive and useful results, right, which we will later on expand using examples, right. So for the time being I am just running through some results, right.